Y16 phase shift in RLC circuit. We have RLC and power supply. The potential of the power supply is usually the sinusoidal function. It can be either cosine or sine, more conveniently e to the I omega t. And actually, this one does not exist in nature. However, we can substitute this one and then take the real part, either real part or imaginary part. Real part of this one is nothing but cosine omega t, and imaginary part of this one is nothing but sine omega t. So derivation of the general formula is usually by making use of e to the I omega t, but it is always possible to derive every full expression by making use of either cosine or sine. In the main text, I have provided all the details by making use of the three distinct ways, and I have shown that the three ways are identical to among one another. If you do the calculation in the current IT instead of Q of t, in terms of this e to the I omega t or cosine or sine, this is the derivative. The inverse, this is integral. When I want to compute the potential difference in here, I have to take the time derivative. And actually, this is for resistor. This Q over C is the potential at the capacitor. If you want to consider the potential capacitor, then you need to know the charge Q. And resistor, you need to know the current. And for the inductor, you need to take the time derivative. Okay? So I, Q, I dot. This is derivative. This is integral. Derivative of e to the I omega t brings in I omega. Integral is 1 over I omega. And 1 over I omega is minus I over omega. So we have negative sign and positive sign. And if you consider current, there is no phase difference. And we know I is actually e to the I 1/2 of pi. So multiplication of I brings in additional phase by 90 degrees. Multiplying minus I, that is the integral of time over time, then minus I. Minus I is e to the minus I 1/2 of pi. So remember this. So everything is based on the current. If you want to consider current, haha, IR, VR equals IR. That means this is a real number. I mean, the reactance, resistive load of reactance is called XR, and this is R. The potential is current multiplied by some load, and this load for the resistance is a resistor is the resistance. This is a real number. L, VL, that is multiplied by L. However, if I use e to the I omega t, derivative brings in I omega. So plus I omega L. I multiplied by I is the current. So this is a real number. And in the case of inductance, I have a plus I omega L. And what about VC? That is a Q over C. But Q is the integral. It is derivative integral of current. That means integral of current, integral of this will give minus I omega. So that's the reason why we have 1 over omega c in the magnitude. But however, if you look at this is actually the absolute value of a complex number. Is R plus I omega L over omega 1 over omega c. This sign comes from this convention relative to the current. That makes the resistance to be real number, and this inductance and capacitance, they become proportional to the imaginary part because of the derivative or integral. Okay? So when we define reactances for our LC, we don't put any sign on it. But when they are being together, then you have to write in a complex variable. If R is lonely, then R. R and L, you need to write it R plus I omega L. And if you have everything all together, then R plus I omega L minus omega C. And R and C only without L, then you need to write this impedance. This is called impedance minus I 1 over omega C. So if they are all together, it is R plus I omega L minus 1 over omega C, and we write it in terms of reactances. That is XR plus I XL minus XC. And then if you are interested in the amplitude only, then amplitude is just absolute value of this complex number. Absolute value is the square root of real part squared and imaginary part squared. Sum, take the square root. And next, we need to consider this real imaginary part. From here, we can determine the phase difference. The phase difference relative to the current. We first consider the relative to the current. We use this minus phi that is different from delta that appeared in the previous analysis for the simple harmonic oscillator, mechanical harmonic oscillator problem, that we were concentrated on the displacement. But here it is in this case it is a x dot. The current I corresponds to the velocity. So when we consider x of t, we usually substituted omega t minus the delta. Here we substitute omega t minus phi, and this omega t comes from the driving force. When the driving force has no phase constant, driving force, this is potential, and this is for current. Current, we assume there is a phase shift by minus phi. Okay, so the detailed calculation has already given in the main text. Let me review the final result. This Z is the absolute value of the complex impedance, and this is real part, and this is imaginary part. So we remember XR plus I, XL minus C, XC, that is this. And if you divide this one by its own magnitude, modulus, okay, this one is called impedance, Z. And XR over Z, this is cosine phi. And this imaginary part divided by the impedance is defined by sine phi. That's the convention. Once the current has the phase dependence minus phi, what happens to Q? From I to Q, what we have to do is what? Integral over time. That is to multiply 1 over I, or minus I, or this is I minus alpha pi, minus alpha pi. This shift has been made due to this integral, time integral, brings in this additional phase difference relative to the current. In the case of inductive load, what we have to do is the time derivative. Time derivative brings in additional factor of I, that is e to the I, e to the I half a pi. That's the reason why we have additional phase shift by plus 90 degrees. Okay? So relative to this one is what? Phase of current. It becomes, cosine becomes sine. This one also becomes a sine. However, we have different sign. Okay? You know why? It is the integral, and this is derivative. If you take the derivative, cosine becomes a minus omega sine. And that omega dependence appears as a, XL is omega L. So that additional omega is absorbed into here. Here, what's that? If you make an integration over time, cosine becomes a sine, but you have additional factor in the denominator 1 over omega, and that has been combined with this one. What's that? Q over C. This C is to be multiplied to omega in the denominator, and 1 over omega C is XC, reactance for the capacitance. All right, so if you combine everything all together, you will be able to find the potential at every point. In the previous class, I have shown how to find the have to find the potential difference between two terminals. So here, if you want to solve the problem, you must determine the direction. You must determine the direction of current. For example, in here, this A is grounded. It is always, its potential is always a 0. Therefore, usually we put the positive sign, although it is a sinusoidal, sometimes it becomes negative or positive. We assume the conventional direction is from here to there. Current flows in this way. Okay, when you follow the current, the change in potential is minus L di over dt. It becomes, potential becomes minus IR, decreases. So current flows, it is a positively charged, negative charged. You pass, you have Q over C minus sign, something like that. So remaining pieces are straightforward once you know the rules. So every steps, every details of calculations are displayed in here, so you don't worry about how to reproduce the final result. This is just for the consistency check. You know, VA is grounded. The result must be 0 always, but this tedious calculation shows that at the end of the day, you will reproduce the simple result for 0. This is true for the cosine case, and there is no difference at all if you consider the sine. And everything is the same. This part, that's fine. Okay, power loss. This guy loses power. These two guys saves the power in the magnetic field, in the electric field, but it is losing the energy all the time. How much? I squared R. And once you know the solution, every solutions are given above. Here, solutions are given, and these capitals represent the amplitude. So these are real numbers, and time dependence appears in such a manner. Usually, we need to know the time average. Once you want to compute the time average, it's good to evaluate the integral over time with a period and divide this one by period. That is the time average. And everybody knows that sine square, this is sine, and sine square is a kind of this kind of form. Its average is just 1/2. High school students know how to evaluate this. So that's the reason why when we consider alternating current that flips the sign plus and minus, then we make use of this factor called RMS. Time average is 1/2, 1/2. At the amplitude level, it should be absorbed into the amplitude by I over square root of 2. This is RMS, root mean square. square, mean, and then take the square root. So it is square, take the time average, that is mean, and the square root becomes 1/2, becomes 1 over square root 2. So that is true for both the potential, every potential of that, every part of the potential of the every part, and the potential of the power supply. So using RMS, we can absorb the time dependence factor 1/2 at the amplitude level. Finally, in an RLC circuit, okay, we have been concentrated on the phase difference. The omega t is the potential of the power supply. Omega t minus phi is the phase of the current, and phi's cosine and phi's sines are completely determined by the reactances and impedance. So finally, this power of the resistor can be evaluated explicitly in terms of the reactances and impedance. If we substitute everything all together inside the expression, you will find that. And actually, this factor is nothing but what we have done with the calculation for the resonance in the simple harmonic oscillator and the driven damped harmonic oscillator. What we have to do is just omega 0 is 1 over square root of LC, and you remember when the amplitude is maximized. The amplitude is maximized for the velocity. For the displacement, the amplitude is maximized not at omega equals omega 0. It is slightly shifted by 1/2 gamma squared, we remember. However, if we consider the velocity, the resonance appears exactly at the omega 0 because the current I is analogous to the velocity, that is x dot. The resonance appears, this, as far as this current is concerned, at the frequency, the characteristic frequency of the simple harmonic oscillator that is without resistance. Okay,